Our final objective for the unit is to review the electromagnetic spectrum, and we'll understand emission of light from an atom. So this is the electromagnetic spectrum. It ranges from radio waves, then microwaves, infrared radiation, visible light, which gets broken down here into our color spectrum that we can see. Then there's ultraviolet radiation, followed by X-rays, and then gamma rays over here. Remember, gamma radiation is high energy emissions. So there's very high energy on this end of the spectrum, which would mean, conversely, that there's very low energy at this end of the spectrum. Like radio waves are perfectly safe for us. So consider that from infrared, the color spectrum goes red, orange, yellow, green, blue, indigo, violet, and then from violet it goes ultraviolet, like the radiation from the sun. So we would like for you to know that on this end of the spectrum, particularly in the visible spectrum, that red has long wavelengths, which means they have a low frequency and low energy. And as I move to the other side of the color spectrum, violet and then ultraviolet, X-ray, and gamma radiation, towards the right side of the spectrum, we have shorter wavelengths, high energy, high frequency. So visible light is part of the electromagnetic spectrum. It's made up of the colors of the spectrum Roy G. Biv. Notice that red is closer to infrared rays and violet is closer to ultraviolet rays. So this is a wave diagram. There are some parts of the wave you should be familiar with. The crest is the high point of the wave, and the trough is the low point of the wave. The amplitude is going to be from here to here, and it's going to be the maximum displacement of a wave from the rest position, or the height of the wave. The wavelength has this symbol, and it's the distance between two adjacent wave points. So, for example, from this point to this point could be one wavelength, or from this point to this point could be a wavelength. Frequency is going to be denoted with the letter F, and it's the number of wave cycles to pass a given point per second. The SI unit for this is hertz. The speed of light is represented with the letter C, and it is the product, or when you multiply frequency times wave. So speed of electromagnetic waves is the speed of light, which is equal to wavelength times the frequency. And I want you to notice that because these are being multiplied to each other, they have what's known as an inverse relationship. So when one of them is increasing, the other does the opposite, is going to decrease. And the same thing in reverse. When one of them is decreasing, the other is increasing. So they have what's known as an inverse relationship. If frequency increases, wavelength decreases, or if frequency decreases, wavelength increases. All electromagnetic waves travel at the same speed, the speed of light in a vacuum, which is 3.0 times 10 to the 8 meters per second. So, Planck's constant, this is the energy equation. In 1900, Max Planck showed that the amount of energy absorbed or emitted by a material is proportional to the frequency of the radiation. Planck's constant is this value here. This means that photons with low frequency, like radio waves, have lower energies than photons with high frequencies, like X-rays and gamma rays. So, its energy is equal to Planck's constant times frequency. There is a direct relationship between energy and frequency. So if frequency increases, so does energy. And if frequency decreases, so does energy. So these are going to be direct. They both increase or decrease together. Atomic emission spectrum. Every element emits light when it is excited by the passage of electricity through its gas or vapor. Electrons start off in their own ground state, which is the lowest energy level. When the electron gets excited, it raises from the ground state to an excited state, or a higher energy level. In order to jump to a higher level, the electron had to absorb a quantum or packet of energy. When it falls back down, it releases the same amount of energy as what's called a photon, and we can see that. Photon is light, so we can see particles of light. And so this would be the atomic emission spectrum of hydrogen, where it's going to absorb some red, green, and violet light, and then whenever it releases that energy back, we see those as red, green, and violet. Electrons can only gain or lose quanta of energy. Electrons make a quantum leap when they get excited and jump to a higher energy level. When they drop back down to their original energy level, they release the quantum of energy as a photon of light. The electrons dropping from different energy levels give off different colors of light. So this electron is at a lower point, and that is considered its ground state at the energy level number 2. It has to absorb energy, like energy given off from heat, for example. And then when it absorbs that energy, it is able to jump to energy level 3, become excited, be at a higher energy state. And then at some point, what goes up must come down. So it's going to go back from energy level 3 down to energy level 2. And in that process, the energy it had absorbed to begin with is going to then be released in what's called a photon, which is a particle of light that we can actually see. So it's releasing energy as light as it falls back down. So we have energy level 1, 2, and 3. Energy level 1 we'll call the ground state, and then these are the excited states, energy level 2 and 3. We have an electron at the ground state, and then if that electron can absorb some energy, this would be a quanta of energy, it would absorb it, and then it would have enough energy to become excited and jump to a higher energy level, like energy level 2. So this is the transition from level 1 to level 2. It got some energy, it jumped up to level 2, and now it's in an excited state. This is an excited electron. It's unstable and must do what? It must go back down to the ground state. But in order to drop back to the ground state, it has to release energy, and when it releases it, it does it in the form of light, a photon, and we can see the color of light that's being released. Depending on how much energy was absorbed is going to dictate how much energy is released, which is going to dictate what color we are seeing. Let's see that again with more energy. So again, ground state, excited state. Now we have energy that is high enough that we can jump to energy level 3. So we transition to energy level 3. This is an excited state. This electron's in an excited state, an excited electron. It's unstable, therefore it's going to have to fall back down to the ground state. And when it drops back to the ground state, it's going to release that energy it absorbed, but this time it's going to release it in the form of light. And it's going to be violet colored light because the energy that was absorbed was enough to raise us up to energy level 3, and so the release was a violet color. This is the atomic emission spectra of hydrogen, and what I want you to notice is that this is the color scheme that is given off by a hydrogen atom whenever it gets excited and falls back to the ground state. And so notice that the violet color is 400 nanometers wavelength. This is 434, 486, 656. The longer the wavelength, the lower the energy. So very little energy was absorbed to jump to here, and so whenever the electron fell back to the ground state, it released red colored light at this point, which is low energy. Whereas over here, violet, 410 nanometers is a shorter wavelength, which is a higher amount of energy. So this is the color with the most energy. So a large amount of energy was required to jump from energy level 1 all the way to energy level 6, which means that the light that was given off afterwards when it fell back to the ground state is going to be violet colored light, which is a light color that has high energy. And so here you can see where the energy is being released and then it gets absorbed by this one. It jumps to an excited state, and when it falls back to the ground state, it releases that energy.